Right, so again, welcome. Today we're discussing the trial map, getting within ARM, getting your randomization set, either to match one you've already decided upon or use ARM to make that randomization in the first place. So to start here, I just have a pretty much a blank empty protocol that's got 12 make-believe treatments in it, just to make it easy for us to manipulate the trial map. So our first scenario, we'll kind of talk through the different ways to manipulate the map that we get within ARM to match an existing randomization that I may have already chosen, or if it's already been, the trial's been planted, etc., then we'll just want to match that in our trial. So of course, when you start with a new protocol or with a protocol to create a new trial from that, I'll use the File menu and Create Trial. And after a little bit of validation, it will start with the first step, which is our trial map. So just as far as setting and manipulating the randomization, you can do this either when you're first creating the trial, as I'm going to do here. It's really nice and easy this way to manipulate and move things around and update our settings. But if you already have the trial set up, pretty much all of this functionality is the same. You would simply open up the trial map from your trial that's already been created, and you can do a lot of these same things. But the only major exception I can think of is once you enter data into an assessment column, then the re-randomize goes away. So some of the just wanting to set a randomization and utilize that, that is disabled just because once there's data attached included, we wouldn't know how to keep that associated with the right thing if we suddenly mix everything up. So outside of that, or if you haven't put data in your trial, then everything here we'll discuss should be fair game on either scenario. All right, so here we are with our trial map. We've got our randomization that we've been presented. And I think the first thing to discuss, I think it's the most common question that we get, is really to change the size or shape of this map. By default, I've got my 12 treatments. If I color by replicate, we can see that I get one long replicate. So it just goes all the way down the field, 12 plots in a row. But that's not always feasible or the case for a trial. We're limited as far as how much space we have to fit things in. Then that's usually one of the bigger questions is how do I change the shape of the map? And typically the number one answer there, if we go into our settings, is to change the block size. So it's about 2/3 of the way down here on our layout settings. And so the block size will determine how many plots wide in that horizontal row, how many plots do we fit in before we start a new row. So in my example, maybe I need to cut that in half, and my replicate actually spans 2 different rows because I don't have space for all 12 wide, but it fits nicely if I do 6 and just 2 rows of 6 for a single replicate. And what I have 4 replicates here, so of course we'll end up with a total of 8 rows. So setting that block size here smaller for me, ARM will regenerate a randomization for me, but now we can see the shape of our replicate and our map overall has changed significantly. We've now limited down to 6 plots, and then we'll finish out the replicate on the next row. And then it just, of course, repeats like we have stacked replicates on top of each other. You can also, so in this case, it is a nice even number, so it makes everything look real neat. few other options though. If we go back and try a couple other block sizes, maybe let's say 5. I'm actually constricted even more. And so with 5 as a block size, things are a little less nice. As you can see, we end up with 3 rows and a bunch of blanks. By default, ARM then will start the next replicate on a new row. And maybe that's the shape of our map. That works just fine. Or if I am restricted in size, it'd be kind of nice to use these 3 plots and basically just start that replicate, my replicate 2 right next to replicate 1, just to really squeeze things in and make the best use of the space I have available. So if we go back to our block size settings, there's an option to fill blocks. So that scenario, that 3rd row where we only had 2 plots and we needed to start a new replicate, turning this on will then fill that all the way out. So it'll condense that map down much nicer. So we can start replicate 2 in this 3rd row, and then just obviously depending on how many plots and how things match up, we end up with the Tetris looking thing here to squeeze things in nicer and save a little space. And on the flip side, we could even go larger. So instead of 12, we had 12 treatments. Maybe we want to fit in 18. So maybe we're more limited vertically and need to fit things in. If you go larger with the block size and how many treatments you have, of course, you'll definitely need to use that fill blocks so that next replicate can start on the same row. So here we have a very long map. We went all the way out to 18 and then started the rest of the replicate on the 2nd line. So now we only ended up with 3 rows instead of the 4 originally. And that's one way to maybe the next most common. If I go all the way up to 24 to fit 2 replicates side by side. That's kind of a maybe more common scenario here where in this case with 12, it's maybe not super practical, but to have 2 replicates side by side and kind of have them stacked. That's one way to achieve that by just setting your block size twice as wide. But especially in this case where that's really wide, I probably don't have a spot that's got room for 24 plots. Maybe we rather would shrink down, kind of like we first started with a replicate being only 6 wide, but then having the replicate side by side. So that brings us to kind of the other category of setting up our map. So let me go back to settings and we'll just start from scratch here, get rid of the block size. Back to our original map. We do have an option for some more manual moving around. So on the properties panel to the right of the map, there is an auto select for move. There's a little box next to it and you turn that on in order to turn on essentially a drag and drop functionality. So if I color by treatment, so we can see kind of how the treatments have been assigned in each replicate, I can auto select for move and drag and drop the treatment assignment for individual plots. So if I click on plot 101, you'll see that the little boxes go around this number 2. So really what I've done is I am selecting the treatment and I can drag and drop this treatment number 2 to whichever plot it belongs to. So if I have a randomization I've already chosen and I have a specific treatments in mind of where they go, I can just kind of drag and drop and put things in the order that I need. This will catch any moving around if it doesn't quite match the design. So you'll notice if I try to move this treatment 9 up to plot 205, my cursor is changed to an X. And when I let go, it won't let me drag that here. And the reason is because this is in replicate 1. Maybe I'll color by replicate so we can see. Treatment 9 here in 105 is in replicate 1. So we can't simply move, we can't simply move treatment 9 into plot 205 because then we would have 2 treatment 9s in replicate 2 and none in replicate 1. And that would break our randomized complete block design that we have in place. So there are some safeguards. It's not letting you move something around. That's because it's checking and validating against the design. Of course, if you do have like a mist spray or something like that, where you do actually need treatment 9 in this physical location, then the way to do that is auto select for move your plot or your experimental unit. So when I do that and click on this treatment 9, it actually doesn't take just the treatment, but the entire plot. So if I switch that here with 205, what you'll notice is that treatment 9 is physically, of course, here in this location, but we've kept it assigned to replicate 1. So we're not breaking our design, just spatially, the location of that plot has moved. And if you're plot numbering, of course, now we have plot 105 way up here. That doesn't make a lot of sense. There is a renumber plots down here. So after making some changes, the renumber plots will then kind of recalculate, refresh, so that way the numbers are logical as to where they are now. And the same thing goes when you're moving. We'll see in a second if we move replicates as well, which is kind of the third component here. I'll start over. I'll re-randomize so we get kind of a fresh, non-moved around map here. So the third component you can move is a replicate. So if I click on plot 201, you'll see that actually not just 201 is selected, but all of the plots in this replicate. So I could drag this, I could switch it with a existing replicate if I wanted. Or if I want to move this to be next to my other replicate, I can bring 201 and I'll just drop it in the empty space to the right of plot 112. And ARM will then add in columns in order to fit that in. And now I can move 401 maybe and put it right next to there if I'd like. So that's another way to get to that replicate side by side. In fact, we can kind of combine those two examples. If I go back to my settings, and let's say we like the idea of a block size of 6 because that squares things off a little bit, makes my replicate not quite as wide, but I still need to have them side by side. I can set the shape of this map, and then we can auto select for move the replicate, and we can bring replicate 2 next to replicate 1, and then 4 next to 3. And there, so now we still have really the same shape as we started with all along of 12 plots wide, but now our replicate is a little more squared out, maybe a little less apt to big changes in the field as it spreads all the way across. So that's the auto select for move. If you're in a multi-factor design, there'll be one more option here, and we won't show that, but there is in a like a split plot design, especially you have main units and subunits, and so you can take a whole group of the main units and move them together as one section, much like we did when we have a replicate that selects more than one plot. That main unit will let you move kind of those grouped treatments around. We show that more in our split plot webinar that we've ran in the past. And I guess just to show as we were moving things around, I was kind of just leveraging the scoot something to the side, and ARM can make room. You can manually add empty spots on the map as well, just by using the right click. So I could insert a column, and that will put in an empty set of plots. And same thing with the row. Of course, you'll notice as I was moving things around, there is an option to auto delete blank rows and columns, which is really handy when you're moving replicates to really change the whole shape of the map. It gets rid of empty space right away. As you can see, then it's also very easy to accidentally, all you gotta do is make ARM think you moved something around, and then that option will get rid of anything empty that you have. So if all of a sudden your empty stuff disappears, that's over here on the properties. Then if you turn that off, now it'll be a lot easier to keep that empty space that you were adding. You can do both rows and columns. And that's actually one way to maybe accommodate a blank spot in the field. You know, so if you can't quite put everything in a line, you could add some empty spaces and then just move around, maybe move around your plots. So if there's just maybe an empty spot right here, I could make up whatever. Maybe there's a whole swath that's something here we can't really put plots or whatever the case may be. Inserting some blanks and kind of moving things around can help you more match the map to what's in real life. And then of course you can also remove some that completely empty row if you don't need it once you've finished moving things around to where they should be. So there is a comment about being able to insert columns or rows as drive alleys. That would be a different size than the plots. So yeah, right now we're fairly limited on the spacing here. We have, of course, the plot size defined. In the settings, there's also your alley width. But of course, that is for every single alley or space between the plots. Or excuse me, the alley would be the space between the replicates. And then there's also an option for the width between the plots. So maybe I'll make these one really large and one small to show the difference. And then I just need in my options, I can draw it to true scale. So this will use my plot dimensions and show those widths. So the alley width here is between each horizontal row that I set to 5, and it'll just match whatever your plot size is. So if you had a plot size in meters, then the alley will be 5 meters, or if you're in feet, then those numbers on the settings would be in feet. So you can see we had 5 in between each of these horizontal rows, and then the plot is that half, I think it was a half that we had in settings, and that's just in between each and every plot. So those are the two options here. We are going to be replacing this trial map here this year. We're just about ready for a beta test for a new geospatial map. And that'll bring a lot of capability to do as Jeff suggested, being able to customize and get things to fit right where they really truly are in the field. So you're not stuck to a grid quite as much as this tool has. So that'll be an exciting development for us this coming year to get that out and get to show that new tool. But for right now, that here we have kind of those two options for you. just to specify your spacing in the map. A great question and comment there for us. Thank you. All right. So I think that covers the majority of our options for kind of manually moving things around, getting the map to fit and set the way we've determined kind of ahead of time, maybe some other tool, or if you manually randomize or things like that, to be able to get that there. In this example, have 12 times 4, not too many plots to deal with. Of course, a larger map, a larger study, it might get a little more tedious, moving things around and matching all your treatments up. So there is one other option for setting up a randomization, matching a randomization that you have. If you have described it in Excel, we'll show that here. There's one question real quick, but before I do that, and it's about the orientation of the map. So let me real quick, I'm going to go back to my settings and we'll start from scratch with no block size. And get rid of the true scale, not that that's too distracting, but back to this here where everything's kind of horizontal. And there is an option instead of this basing our blocks horizontally. And of course, we could change the shape to match. We had a different shape, but there's also an option to make the blocks vertical instead. So, everything so far, we've really defined the block horizontally. If we change the size of the block, that's the horizontal number of plots in a row. But we can actually kind of tip that all on its side and rotate that 90 degrees. And that is back in our layout settings here. There's an option at the top for blocks as columns instead of rows. So as I said, that really is going to rotate our map 90 degrees. So you can see instead of very wide replicate, we actually have a very tall replicate now. So that is that option to really twist things around. We can still do a lot of the manipulation we did. So maybe if I set this to 6 for our block size, we can see what will happen. Still kind of that same concept. Our block, is still going along with our replicate, but again, this is columns now instead of rows. So we're setting how many plots can be in a column, and then we continue to move to the right. So, here I had a very square number, 12, easy to divide by a few different things. So there's probably multiple ways to get a map that looks similar. But I think it would just be important to make note of what is the direction of my blocking, especially in the RCB design, that blocking is important. So that might be actually the first option you'd want to consider before moving some other things around, is to use this option if you are that kind of operating at that 90 degrees, if you will. So good question to show that. All right, so last item on this topic is using Excel. So let's say I have decided my map already, or maybe it's been given to me from somebody else. We can actually use Excel. And so we can really skip over this trial map entirely. So especially when first creating that trial, I know I already have it defined somewhere else, then I can just accept current and move on. And we'll show this process for matching your trial. I'm not going to bother saving the file here. We can actually set up the entire trial map all in one go by utilizing Excel and copy and pasting with ARM. So what I have here is an Excel spreadsheet. And the key here for doing this is to make sure to use headings so ARM knows what information we're going to be giving it. So I have a list of plot numbers and the treatment numbers associated with each plot number. And so what ARM can do, and maybe I'll start with just the first four here. What ARM will do, since we have used these headings, it knows that we're not going to be pasting in data. You know, if we didn't have any headings and we just took these numbers and went to copy and paste into ARM into an assessment column, then it's just going to think that those are assessment values. So they're just a list of numbers. You must be bringing me data. Of course, that's not what we want to do. So instead, in our Excel, we want to make sure to include those headings when we copy, so that way ARM knows these are special pieces of information and will actually look to our randomization instead. So when I copy and paste with those headings, and I'm just picking an empty assessment column to paste into, then a warning comes up and ARM has matched, it recognized our plots and our treatment, and it says that in this trial, currently treatment 1 is assigned to plot 101. But in that Excel file that we just pasted in, treatment 11 is associated with plot 101. So it's asking if we want to change the randomization to match what we pasted in. Now, in my case, I think I have a slightly different shape. So not all my plot numbers will match. So that's why I only chose those first 4 plots, just to kind of demonstrate this. You'd want to grab that whole list. Otherwise, we'll probably make a mess here and it might yell at us. At least it didn't just yet, but it probably will soon. Anyway, so now it has updated the assignment of that plot based on plot 101. It has put the treatment number to match what we pasted in. And I'm sure it's going to be mad at me perhaps. Well, it did it okay. It would get mad if we tried to save, because you'll notice I have 2 treatment 11s now. I kind of have a mess because I didn't paste the whole thing. But at any rate, you can see that the trial map that we worked on here is reflected in this data section. So this is really just a text-based version of the randomization on our map, where the block and column is essentially the XY coordinate, if you will, on the map. And then of course our plot number and our assigned treatment. So now that we've pasted it in, we've updated what treatments are assigned to those first 4 plots. And I really should do that with all of them, so that way we get a complete randomization and not the mess that I currently have right now. And the reason I have this mess is because there's one other example. You could actually really change the entire shape of the trial map if you include the block and the column values as well. So here, now I have all of those columns, the XY coordinates, if you will, the replicate assignment. So that way, kind of like when we saw the coloring by rep, we wanted to make sure that we had one treatment in each replicate, things like that. Wanted to make sure that that is valid. So now if I copy this entire set of information in and paste, again, we get the warning that is recognized there's a different randomization pasted in. So I want to say yes to update. And you'll see then that that list updated. And in fact, my trial map will be a totally different shape even. I don't know what my example, I'd use an example from yesterday, but clearly I did something not quite right when I pasted those values in, because things are moved around a little stranger than I expected. But at any rate, that's really the method for updating your randomization, whether you use just the plot and treatment to just match, to get the right assignment to the plot, or if you expand and do the whole shape of the map by bringing in the block and column and replicate values. And one note, if you are using a different language in ARM, here, of course, I'm operating in English, but you can use other languages as well. If your ARM is set to another language, just follow the headings. So that was really what I had matched in my Excel document. Rep block, column, plot, treatment. So if you're in a different language, just look to what ARM is displaying right here. And you can use that same, I think they're all just 3 or 4 to keep it nice and small. Just match those values and use that as your headings. And ARM will do the very same thing, match things up and update the randomization. All right, so that's how you can use Excel to match up, maybe save some time and prevent a manual moving back and forth. All right. So that's our first topic, was really having a map already known and just getting that to match. I'm just closing the trial, coming back to this protocol so we can repeat the process of creating a new trial, this time to utilize ARM's randomization tools and talk about what we can do as far as allowing ARM to randomize and use the randomization ARM gives us. So we're presented with our trial map. You'll notice every time we came back and forth after we changed a setting, all of the numbers typically are different. And that's in that new protocol process, there's a whole lot of re-randomizing that happens. Once your trial is set, of course, we're not going to suddenly randomly move all the plots around, but this first go ahead of generating a trial, it's really all about the getting the map, setting the map, that initial time. So the randomization, of course, we really would want to maybe inspect, because to be totally clear, the term randomization maybe isn't exactly what researchers want. From a mathematical standpoint, random would be, even if you had treatment number 1 in the first plot in every replicate, that could technically be just as random as what we see here, where they're spread out more. So really, in actuality, what we're looking for is a dispersion of treatments, and not really just a randomly selected combination, where we really want the treatments to be dispersed nicely. And so, of course, we can color by treatment, and just kind of eyeball and get a feel for maybe what we have in this randomization. My eyes kind of gravitated towards these 8s here. They're all kind of close together on this side of the map. Maybe the treatment 5s are almost like that. So, we could say, well, I don't feel super great about that. Let me just re-randomize. And ARM will just randomly select another randomization, move things around, and we can just spot check again. I don't see any streaks. Too bad. This feels pretty good. You might be maybe a little limited as far as just trusting your eyes. So we have a quality tab that can kind of help us analyze this randomization that we've been given. So the first tool we have here on the left is a block size, suggesting a block size for us. So we've kind of showed before, if you're just restricted in the area you have in your field, you might be forced into a particular block size. But this tool is really specifically planning a block size with the goal of limiting how large our replicate is, or maybe not large, but how it spans across our trial. So right now I have a replicate size of 12. Our block isn't limited in any fashion. And ARM is actually going to draw for us the shape of our replicate using that true scale option, taking into account any of those alleys and plot width that we had defined to calculate what that shape is. And you'll notice for 12, it's a very long rectangle. So if we're out in a field, you can imagine how much how much area that really spans down the trial. If we're really at all concerned how consistent maybe the soil and the conditions are across that entire area, do we feel really great that plot 101 is really going to be under the exact same conditions as plot 112? Because after all, that's the goal of the randomized complete block, is that all of the plots within our replicate are as fairly treated as we possibly can. So that way our treatments are the only thing really different in the area, and thus we can get a real good sense of what differences are among the treatments. So the concept is, well, maybe we don't feel super great because in a field, there's only so much we can really do in some of the aspects of the trial. So if we instead consider a block size of 6 or a block size of 4, you can see as we change the selection, the shape here on the right updates to give us a sense of the different shapes. So 4 is maybe a little better. It's still kind of a rectangle going the other direction this time. But really what we're trying to do is maybe find the most square that we can. And actually a block size of 6 does a really nice job of that. Looks almost like a perfect square. And this table has all of the values ARM has calculated. So the width of the replicate, the length of the replicate, and what we use to determine how close to a square it is by dividing the perimeter, or your surface area in a sense, divided by the area within that shape. So the smaller that value is, the more perfectly square it is. So that's kind of the stat, if you will, to decide exactly what is most square. And so we have an asterisk next to the smallest one of these choices. And so that number 6 here gives us that most square option, and thus it is the optimum. Naturally, you can still choose whatever fits best in your trial, but hopefully this tool gives some options to compare and contrast and decide the best option, combining the limitations you might have in where it's going to be located, but also trying to give that best shot at homogeneity within that area. So if I click apply with that column 6, so just as I'm clicking in this table, it's changing that selection. So I can hit apply, and that will change the block size setting. Instead of having to go into settings and setting the block size manually, that sets that for us. just a color by replicate to show. Same thing as when we were changing manually in the settings our block size. So that's the first tool. Again, just to try to quantify and help give a sense of that shape and try to get the most square replicate we can, and maybe combining that if we still have a specific shape that we need to meet to fit in our field, just consider that we can still then move our replicates around. So we can maybe achieve that very nice square shape, but still have that same overall trial shape. If this is what we still have the 12 by 4, that really is what we need to slot in to our field, we can still achieve that goal by moving around the replicates. And yet we've kind of improved our design and maybe our statistical power at the end of the trial by squaring that off. The other tool here on the right is a table really looking at the treatments and that treatment dispersion we had mentioned a minute ago. So let me toggle to look at that treatment, how they are assigned here. So there's a couple of tools here to look at the way the treatments are distributed here on the map that we have. And the first one is the edge effect. So ARM will calculate how many times a particular treatment is on the edge of the trial shape here. So treatment 2 is only on the edge once, whereas treatment 3 ends up being on the edge all 4 times. Now, in some trials, this might be irrelevant if you already plant a buffer around the trial, if there really is no real concern that there could be a difference in the conditions that the outside plots might face versus an inside plot, then we can ignore this column. But certainly, if we were at all concerned that there may be an edge effect, clearly the randomization as we have now would not work great. So the largest number is bold, and you can see both 10 and 5 and 3 all have all 4 on the edge, and yet the smallest ones are in italics. And actually we have a 0 here. That probably should have been italicized. So 7 is never on the outside. So definitely something that could be looked at. If you really don't like that, of course, you could always just re-randomize, and it'll generate, again, a totally new map. The one downside, we do lose our dragging and dropping by doing that. But if we just move, just for example's sake, I'll just move these again real quick. And you'll notice each time a movement happens, this table is updated. But in this case, it looks like we did a lot better. There's still one that has 0 and one that's got 4, but a lot better on the whole. So we can utilize that re-randomize just to start totally fresh. We don't like something that we find doesn't really feel fair. Just re-randomize it and start again, essentially, until we find one that fits us well. A question here about adding guard rows to the ends and edges. So there is an option here on the properties for border plots. So of course, by default, it's at 0, but if I put in 1 or maybe even 2, this will add those empty guard rows, in this case, all the way around. Let me zoom out so we can kind of see that whole map there. So that added 2 rows and 2 columns, 2 all the way around the field. If you don't quite like that or need it more custom, of course, you could just manually add. If I go back down to 0, you could always add in rows and columns as well. So, we could always do that. Oops, I've got the auto delete again, but you could manually delete those, add those as well. But yeah, if you're going to have a whole border around there, that border plots, it's kind of nice and slick. All right, so then the other calculation here on this table, it's really all four of these are combined together into one idea, and that is to try quantifying that distribution. As we said, really you don't want it fully random, you actually want it fairly distributed across the trial. And so, we kind of mentioned that eyeballing, oh, I don't like that treatment 12s are really close to each other, et cetera. You can really actually kind of quantify that with these calculations. And this is the average distance of treatment comparison. So I've got a slide here to kind of talk through the math of it. I'm a math nerd. I'll try not to get too far into the numbers, but just to show what we're doing in this calculation. And it comes from Van S of Cornell, had created this calculation. And the goal is, again, just to get a feel for how evenly dispersed the treatments are across the map. So we kind of go pairwise across each pair. So let's look at treatment 1 to start with. And treatment 1 versus treatment 2, we calculate the distance between treatment 1 and treatment 2 in each replicate. So of course, in this example, I've got 5 replicates, so we have 5 distances to calculate, and then we'll take an average. So we get a sense on average, how far away is treatment 1 from treatment 2. Then we'll do the same thing with treatment 1 and treatment 3. Take those distances and average them out. So then we have a number for how, on average, how far is 1 from 3, and 1 from 4, et cetera. So then you've got 6 averages of how far 1 is to the rest of the other 2 through 7 in this case. We take the average of those 6 values, we get this average distance of treatment comparison. So overall, it's typically how far away treatment 1 is from any other treatment. And then of course we can do that with treatment 2, 3, 4, et cetera. So that is what's labeled in ARM as average distance. So the goal, if we go back to our ARM, then the number itself doesn't matter much. It's totally going to depend on your plot size and things like that. But what we're really striving for is consistency. If we had a perfectly balanced where everything was exactly as far from each other as one another, you'd have basically the same number all the way across. And so we're looking for big differences. So I can see the smallest in italics is 29. So treatment 6 on average is closer to the other treatments than treatment 11, which actually has the largest. So on average, treatment 11 is farther away from the other treatments. And to kind of quantify, or to give an example of that, you can see treatment 11 ends up being on the extremes. It's the first plot and it's the last plot in 3, I guess this one's here in the middle, but in 3 of the 4 plots, it's on the way edge. So that's why it's so much larger of a value. Compare that to treatment 6. And actually, we could even color by current treatment to kind of leverage that. Treatment 6, on the other hand, is always kind of in the middle. So it ends up with a smaller number. So again, the number itself, not super significant, but the consistency of the numbers and how extreme one is to another. It gives you a sense of how well it's distributed. So again, not a slam dunk, not one thing you can just press a button and boom, here it is. It'll tell you yes or no, maybe a little bit more nuanced, but at least an effort to describe and put some numbers to that concept of just eyeballing a randomization. And so then back on that quality tab, that's that average distance value. There's also a standard deviation, a minimum and a maximum to let you dive in a little deeper into that distribution. How consistent are those versus most extreme examples in each case, all those comparisons. So the goal, again, just trying to put numbers down to that eyeballing effect. And if you don't like what you see, hit re-randomize, and just try another randomization and get a sense then of how consistent things are. This one looks a little better. 34 is the highest and 28 is the lowest. Maybe we feel a little better about that, but that's really the goal there, to put a number to that concept and try to avoid having streaks and things like that. One more option. Yeah, there was a comment here about the block size. That is the number of rows. So the block size is, or not number of rows, number of plots within a row. That's what that block size is. So there's one more option just in this realm of randomization and having ARM generate the randomization for us, and it is this treatment adjacency. I've got a little slide to try to demonstrate what the goal is here. So the treatment adjacency option is, the goal of it would be to restrict the randomization that ARM displays for us with the goal of trying to improve your distribution, specifically avoiding a straight shot, something like this, where you end up in two different replicates, you have the same treatment right next to each other. So by default, the adjacency is turned off. It's set to 0. There is no checking. All treatments put in randomly, and there is no checking of what might happen from replicate to replicate. So something like this, where they just happen to touch, they're in totally different replicates. That just happened that way. There is nothing ARM is going to stop and prevent that from happening. If you set the adjacency to 1, now this map would be rejected. When ARM is generating that randomization, it just randomly picks, and then if it doesn't fit the right conditions, it just re-randomizes and just keeps doing that until it finds a combination that fits the rules that we have. So far, the only rule has been our own design to make sure that fits our design constraints. But putting on the treatment adjacency adds one more constraint to prevent these straight shots. So if a map like this were to pop up when it's generating and we had the adjacency set to 1, then ARM says, no, this isn't valid based on my adjacency restriction, so give me a new randomization. It'll just keep going until it finds one. And so the adjacency of 1 then prohibits that straight shot. And the very closest you could have is 1 plot apart from replicate to replicate. So here you can't have the plots touching, so this would be the closest treatment 4 can get to each other. This is the closest treatment 3 could across the randomization or across the replicate. In theory, if you were to set the adjacency to 2, then that would mean treatment 4 would have to be at least this far away. Of course, there's a practical limit because in this example with only 5 plots, there's nowhere else for it to go. So there's a limit. I think it's 1/3 of the randomization or 1/3 of your number of treatments. Otherwise, you can't. There's just no combinations then where you can actually fit it onto the map. But that's the treatment adjacency. So just another tool. Again, there's not a whole lot visible here for what that does, but it does impact that randomization. So here, there's no way those 12s could have touched. But if I do turn that down to 0, then we'll see when it generates a randomization, if we get lucky and have, there, oh, we got lucky. We had treatment 8 ended up touching, and that's across, of course, it's across replicates. Just so happened that those two were a straight shot. So turning that adjacency on can help avoid those things. There was one question I didn't want to ignore before we were done. Let me get into this trial. It was just to touch again on these values here, and it was the difference between replicate and block. So the replicate is the assignment of that treatment within the design. Remember when we were dragging and dropping, and ARM wouldn't let us move a treatment sometimes because we can't have 2 treatment 4s in replicate 1 and then 0 treatments in replicate 2, things like that. So that is really within the design. Where is the replicate? What plots are assigned to what replicate? The block kind of pairs more with the column, in that is the location of this particular plot on the map. So if we look at plot 201, you can see the block value is 2. So the block would be which row, kind of your x coordinate, y coordinate, if you will, in a coordinate system. Which row is it in? So here it's in row 2. So that is block number 2. And then of course it's in column 1, which is your x coordinate. So that's in the first slot there. Compare that with like 305. If we scroll down to plot 305, it is in row number 3. Bring up my trial map again. It is in that block number 3. So it is 3 up and then 5 over. But it's still within replicate 2, because in the design, we have the replicates being assigned as part of our RCB. So, a lot of times it might kind of match. If you don't have any block size, the two of them might almost be the same. Just depends on your map layout. Okay, well, we've reached our time. There was one comment about a non-randomized block, but I think we might kind of run out of time. I don't want to hijack anyone's time, so appreciate everyone joining us. If you do have additional questions or have some troubles trying to get a map set up, definitely reach out to us, and we can try to help set up your maps for you. But again, thanks everyone for your time, and hopefully we'll be seeing you again at a future webinar.